Hi guys, this is Novitoll. So today we're going to talk about exploiting Linux kernel using CVE 2019-2215, also known as Android bed binder. And I've actually already explained it, the exploitation itself originally found by Maddie Stone from the Google Project Zero. And I explained this in my Twitch stream back in December 2019. So here is the video that I'm going to upload as well on YouTube, but it's in Russian. And here on the live, I kind of reproduced the same issue using my VM. This is a Linux kernel 4.14 using the x86 64-bit system. And I disabled the patch there and some one XSLK feature. So by doing that, I was able to get root and the actual override some preamp segment in kernel. So you can just check out this video if you Russian, and if not, there are, I think, a variety of material. I'm not sure whether it's on YouTube, where explaining this exploit from the very beginning to the end of the exploitation in English yet on YouTube, but in Russian. So I'm just uploading this what I did in December. In this video, I was debugging in kernel. I kind of showed the techniques in debugging kernel. I mean, actually, it was kind of my first experience with debugging kernel, so that's why it's, I guess, lasted for 2 hours, because I was maybe kind of slow, but maybe I was just too, petty to explain everything. Starting from the syzkaller, so here in this video you will kind of be introduced with the Linux kernel exploitation, how Google Project Zero find these bugs, and how can you, apply it to them, apply your knowledge, exploitation, and use these bugs for using the vulnerability for good terms, for sure. And at the end, I guess what I did, I just I hope so, or not. Yeah, let me just go over this. What I did, I should have overrides my yeah, I mean, but the end of this video, I guess it's kind of was streamed badly. Maybe I will just restream it again, because it's really kind of cool exploit. So cool because you can find, this is my original slide. So cool because you can find many information that's popped out on the internet due to this vulnerability. Like, for example, guys using this URL, they made even the kind of course using Linux kernel exploitation, because this exploit actually gives you permission for arbitrary kernel reads and writes. So you can read any memory of your kernel, you can write any memory of your kernel, you can override the address limit. We'll go over this in a minute, and it's a really cool exploit, and you can bypass any security using writes, offsets. And recently there was also the published these exploits where using this vulnerability, I mean using the CVE, you can root your Samsung S8 device bypassing DAC and setting CLinux to permissive, and bypassing Samsung Knox, and real kernel protection bypass as well. And yeah, but the let's just start from the very beginning. So Maddie Stone also presented this CVE in offensive account, I guess. So this is 2018. No, this is not this one. It should be, yeah, this one. So April 17, kind of fresh. And she also, I guess, showed this she was presenting the same exploitation somewhere else. But yeah, the exploit is very interesting. So there was initial reports in Google Project Zero by Maddie Stone in September 26, 2019. So here is the POC, and the very interesting story of this exploit is that the issue was firstly introduced I guess in November, somewhere here. Yes, I guess somewhere in November by syzkaller. So what syzkaller is, let me just go through briefly with syzkaller. This is the syscall fuzzer product by Google. It's open source, a really cool product. So it's kernel fuzzer. What it does is just like, you know, randomly, I mean smartly or randomly, not like pure randomly, but in smart way, it just like, you know, sends syscalls with the random parameters, again with the smart random parameters, and just crash your kernel. It can fuzz with that way variety of operating systems like listed here, and there is also the kernel. Oh no, wait, it is a syzkaller Google Apps bot. There is the sysbot that's running on the Google Cloud Engine infrastructure that's periodically, not periodically, but like a 24/7, I guess. That's the kind of nice explanation. They actually keep fuzzing the like latest mainline Linux and other kernels as well, and try to find bugs. And it just really kind of briefly explanation what this syzkaller is, and it's also like every kernel is compiled with the KASAN, and KASAN is kernel editor sanitizer, and when the sysbot crashes the kernel, it gives you the kind of, you know, typical KASAN output, which is very, very useful, and we will try to also go through briefly how to read such as reports. So back to our CVE. Again, to the interesting story is that I guess it was November, I'm not sure the correct date, but like in November 2017 was syzkaller initially reported this bug, because this is how actually the process works. Sysbots, if founds the kind of bug, and it's in the Google group, it's like starts the kind of separate conversation and uploads there the crashed output and assigned to maintainer, I guess, and the maintainers are notified. And it was patched in 2017 in December. But yeah, it's also like in the 4.14 LTS kernel, and Android 3.18, 4.4, which is, I guess, for the Google Pixel 2 or 3, something like that. So it was kind of back patched by LTS kernels, but it was patched, but the secret built-in was kind of late or maybe misused. I'm not sure what was the right story. You can like check on the SoftSafCon video, what Maddie Stone recently explained it. So it kind of was in a while. She also kind of said that it's not kind of 0 day, it's kind of like 657 0 days, something like that. So where is the exact video? Yeah, she just explaining the same thing that I'm going to explain you, but I will do maybe more in like with more technical backgrounds, with more technical details, I mean. So yeah, and here are the list of the affected devices, and here we are going to face first Linux kernel exploits, and it's starting from the user space. So as you know, prior to getting to this kind of exploitation, not like kind of level, but kind of exploitation degree, you need to like understand how the user space communicates with the kernel space using syscalls and what a syscall is. And I think this kind of exploits helps you. You have enough theory backgrounds, but it helps you to practically understand the internals of Linux kernel. So if we go through like briefly by POC, the POC is very like the POC, what I meant. It's really simple. It's creates the file descriptor for the binder. Binder is basically IPC, inter-process communication for the Android. That's it. So you create file descriptor, and yeah, for sure it has like its own driver. That's for sure. And we'll go through our code where found bug. We will see the place in this driver where you can see the bug where it occurs. So you open the file descriptor of your binder device, and then you also create your epoll. Epoll, for those who don't know, it is the syscall that's doing the polling. It's kind of optimized its way of doing. If you're familiar with the select poll syscalls, so epoll are doing kind of efficient, because it's like it does not like efficient way in terms of many file descriptors. So you're doing this event poll. I mean, you open the file descriptor. This value is I mean, it just if you go through the man page, it says like just like it needs to be just bigger than 1, so it doesn't mean what the size is, I guess. Size. Yeah, since Linux 2.68 argument is ignored, must be greater than 0. So we just create our event poll file descriptor as well, and using the syscall by flag epoll adds, we just kind of tied these two file descriptors using this event. So we are doing this, and then to destroy our binder structure, we are like initiating with the syscall iovec by passing the specific parameter. So what happens when you're doing this? We need to get, I guess, introduce ourselves with the binder thread structure. So now let's just go through first with the syzkaller reports. So when syzkaller reports puts these outputs, it's kind of like relevantly easy to read, I guess, because it's real. I mean, not easy, but it's a really useful report by syzkaller. So this is the KASAN KASAN outputs, and it says that there is the bug called user after free. So user after free is a typical heap space vulnerability where you have it kind of when you have yeah, I guess I need to just to explain everything just to make sure that everybody understands, and I don't know what the audience is. So for the use after free, if we go into very briefly, you have some buffer, and you are allocating some space for this buffer. Then you free this buffer, but there is some logic in your code that's still using this dangling link, using this buffer. So it means that it has the same pointer for this space, but your buffer is already freed. But if you will try to address on this buffer or kind of use this buffers, then it's kind of used after free vulnerability. So syzkaller noticed that and reported it in such a way, and it's kind of puts you with the KASAN output. So you're going to this is the call trace. You're going from the bottom to top. So this is how it actually was kind of triggered. So you're calling the event poll. Event poll calls the free event poll free unregistered poll weights, remove weight queue, and here you have the remove use after free vulnerability, which was occurred in this function. You also can see the allocated by task, freed by task, how it was freed. It was freed by a iovec wrapper for the binder driver, where you actually doing this release, and it's inside of release you're doing dec temp tref. And another important part is that it also shows you kind of the buggy address where it belongs to. It means that you have the binder thread structure is the 512 bytes for this specific version of Linux kernel, and the kind of after, like, freed address is 176 bytes offset inside of this buffer, which means that if you go through the where is my slide that I showed in December for the guys? So yeah, Maddie, so here's your exploit, I mean here POC, where she overrided this preamps kind of message in kernel. So yeah, I guess I should have started with this slide. I'm going, like, I'm jumping from theme to theme, but let me just go through, stick to with these slides and just go through over it. So again, for the KASAN, this is the kernel ASAN, kernel address sanitizer, and if you compile your Linux kernel with KASAN is not set, which means let's disable it, and with the enable it, you will see that in kind of enabled KASAN, your kernel has kind of these injection kind of functions that's actually watching your buffer, and it happens something badly with the buffer, like in vulnerabilities, kind of overflow, heap, use after free, double free, null pointer, dereference, etc. It will tell you, it will crash your kernel, and it will report you. And for sure, the compiled kernel with KASAN is, the size is bigger on file systems than normal because of these kind of injections. And yeah, again, for the syzkaller reports, how we just briefly went through, you can see there is the call trace, and there is the free task, and there is the kind of buggy address showing you the freed location, freed offsets inside of this location. This is the POC that we just went through, and yeah, in the binder itself. So what happens that when you sense ioctl with this binder thread exit value, there is the wrapper for the binder driver for the ioctl syscalls, and when the command is binder thread exit, it's calls this function binder thread release, passing to the parameters the binder proc, and the important part, the binder thread structure here on the second parameter. If you go through to this binder thread release here, you can see there is the called function binder deck thread deck strem, if I can pronounce correctly. Yeah, and inside of deck temp tref here, you can see there is the function called binder free threads, which is actually passing the same parameter thread here, and inside of this free thread, it's actually like a free. So we need to go through this binder thread prior to this wait queue, I guess. Let me see what I did that. Yeah, so this is the binder threads kind of compiled version. This is output of program called Pahole. Pahole actually shows you the offsets and the size of each field inside of your structure, very useful tool. You can also check by print k in your kernel using offset off. So there is the binder thread structure, and this is the wait queue 24 bytes object, which is actually freed, and the offset for this wait queue fields is 160. So this is the in Pahole kind of style. This is the offset table, the offset column, I guess, and this is the size. So as you can see at the bottom of this binder thread, there is a very cool task called task struct. It is actual pointer, and offset is 400 bytes, and this is the 64-bit system. That's why the pointer size off is 8 bytes, and the entire kind of structure size is 408, because I guess I'm using some 3 points version Pahole. Kernel version. The idea is following that. Let me go through another slide, and then we'll go back to the wait queue. The idea is following that we want to make sure that this wait queue is not overridden by our exploits, because when we call the binder set exit, remember ioctl, we actually using the we are freeing this object bind threads, but another our event poll or is like using the pointer to this wait queue. So if you go back to the wait queue now, wait queue structure is 24 bytes structure. It has pin lock, which is the 8 bytes on the first position. Then it has the doubly linked list head, and list head is like a list next in pref. Again, so this is the where freed kind of object inside of a bind thread structure is used. When you unregister your event poll, it calls the remove wait queue. The remove wait queue calls remove wait queue. Here is the actual kind of code trace, and at the end, it's just kind of deleting every kind of entry of your doubly linked list. And here you actually how you kind of trigger this this bug, this vulnerability. Yeah. So the patch was done with the following, that this is actually, I mean, this the second box. This is the second patch, which is depending on the first patch for the race condition, due to race condition. But the initial patch was just when you are releasing your binded thread structure, and if you can see that there is still your binded thread is still like using. It's still kind of it's still inactive, like it's still used by somebody. Then you just like call the function wake up poll with these bit flags. This is how it is patched, and in order to exploit the current in order to exploit, you can just download the latest, not the latest, but like a 4.14 the iOS Android open source project source code of Linux kernel. You can in this file binder.c inside of the drivers directory, you can just comment out this patch and just rebuild your kernel. And there is also another thing that you need to do if you are on 4.13. So in 4.13 there was thing called XSOK. So yeah, as you can see in 4.13 release candidates 1, inside of the iovec C file, for the every copy out and copy in, this is the functions that use it inside of known copy from user, copy to user. So if you ever write some driver in the Linux kernel, and if you use copy from user or like copy to user, now inside of these functions inside of the kernel, starting from the Linux kernel 4.13, there is a specific check with this XSOK, checking that you cannot like write or like read like the Linux kernel space. So there is the two constants inside of the Linux source code called kernel ds and user ds, and it basically means that there is a specific delimiter, so kernel ds, like where the kernel actually located, and it's starting from the higher address, from the FFFF, and the user ds is basically kind of there is specific field called address limits, and its address limits is what kind of tells you what is the kind of limiting of this user ds inside of the kernel ds kind of address space. So I mean, not inside of, but like it just basically separates you to the two memory space, and there is the kind of separator. So that's how actually you can control by using these two copy out and copy in functions. And so in order to bypass and to exploit successfully on 4.14 AOSP source code, you just needs to like either not like either, but I guess you just needs to comment out, make sure that this is always true, like if one, so make sure this is always true, and here it's always true when we actually copy in from user space to kernel space, and we are copying from kernel space to user space. So this is my debugging as again I did in the last video, and then the strategy is following of the exploitation. You are using a specific structure called iovec. Iovec is a very cool structure because it has 16 bytes of data. The first 8 bytes is just the pointer iov base, and the second one is just iov flanks. That's it. You just need to override every field inside of freed structure bind threads with these iovec structures with the 000s, and calculate the offsets until the weight q head, because you don't want to override the fields that is used by event poll. So you're just going through here with the zeros, then you are calculating here with the offsets that you just want to make sure that you are controlling these bytes, and then you just filling the rest of the fields again with 0 until the last task struct, because you just want to leak the task struct pointer, which with this task struct it gives you the root for your root. It will give you kind of the direct way for the root escalation. Because here inside of task struct it has like everything: your credentials, your effective user ID, group user ID, your other security permission, other security flags, the Linux, all inside of this task struct. The address limits also inside of the task struct. If the there is specific config file, call it I guess something like config threads info in task struct, something like that, but you can find out. There is we can just go through over it, find it in the internet, but in most of the Androids like REM, what I noticed is that the thread info structure, which is inside of the thread info, you can find the address limit which you want to smash and override with this value in order to user space can access any can send and access any address. So this thread info was not in the task struct, it was in the stack, and you need to like leak the first kernel stack in order to find the thread info inside of your kernel stack. Very kind of complicated, but we will see with this exploit that was actually not this one, because you can also find the another analogs, but this I guess was kind of a little bit cool because I just recently checked it and it's kind of fresh. So yeah, let's just go through our exploits. We commented out our patch. We put some here print.k kind of logs in our kernel. This is inside of the binder C device file. Now what we need to do is debugging, showing how the actually freed how actually like a freed things works. For example, let me just go through it. So I'm sending here now it's going through, but you can see just so this is I put the breakpoint here inside of the kernel address, and this is my payload that I'm sending, and I put it here as a breakpoint, and I'm watching this specific address be fed, and after use after free it's used by it's put here the wait queue I guess previous pointer, which is pointing to this address, and this is the spin lock of the wait queue structure. This is the kind of exploit strategy. It consists of the doing like a fork it two processes, parent and child. So in child, first in the parent, I guess I need to start first with the child, because first you're doing the child, you sleep for 2 seconds, then you sleep for 2 seconds because you need to free your binder thread structure. When you're doing this, your binder thread structure is freed, then you are now using it, the free structure, by calling this kind of call trace of event poll removed by specific ioctl, by specific syscall that I will show later. And after that, you're just doing write v and read syscalls, blocking two syscalls. With the write v, you're actually reading from the kernel space, and from the read, just like reading your buffer that was written by kernel here. And the offsets are very crucial in this exploitation, because if you just kind of go over your free structure, you will affect the spin lock inside the wait queue inside of the wait queue. So remember, inside of wait queue structures, the first 8 bytes is spin lock, and if the spin lock value is not 0, then it will call the CPU stall, which kind of frees your CPU, and it will call the kind of kernel panic. So we explained about this is okay. I will not show any demo because again I already did that, but I'm going over through these exploits. I guess I will go over through exploit by Maddie Stone, so what she attached in her report. So she attached this exploit that basically just overrides inside of kernel the preempts, I mean the UTS version of your Linux kernel, which is proves that you can arbitrarily read and write inside the kernel, and after that you can just basically disable all your security and get root. So we just go through over these exploits. I kind of maybe found a little bit confusing, but I found it very very nice and very cool exploit. We can ignore this. It's just only for the dump. We have our binary thread exit, which is actual constant from the Linux kernel source, but we are kind of make sure that we're using the same value, because we are using the same binary thread exit here when we want to free our binary thread structure. We have our size binary thread structure. Then we are sending 25 iovec structures, and we're putting them in array. Here how we calculate. So we want to control all 190 bytes in hex of freed binary thread structure with our iovec. So we are sending 25 iovecs. It's kind of technique called heap spray also. When something is freed inside of the heap, you want to leak some data that was written, that was used by another software, another function. So you're using kind of a heap spray here as well. But when you do heap spray, you can do by char buffer, or in smart way you can do with the iovec, because iovec is 16 bytes, and yeah, as you can see, we just calculated it as well. Wait queue offset, it's freed. Not freed, it's used objects inside of freed binary threads. This is the offset inside of the binary threads. This is 160, and yeah, just kind of position inside of this array. So again, ignore this. We creating our epoll events. We are kind of making where is the main function? So here is here is the main function, and we create our file descriptor of the binary device, and then we are creating our event poll file descriptor, and then we are calling this leak test struct, because we want to leak this task struct. And then you're allocating iovec array with the size, so you're basically 25 elements of iovecs. Your mem setting for the zeros, everything now here in our zeros, and then for the specific tense location, because again we don't want to override where it is. We don't want to override wait queue 24 bytes, and we don't want to override task struct here. That's why on the 10th positions of the zeroed iovec array, which is like a basically again, iovec is a structure of two fields, iovbase and iovlen. For the iovbase, we're putting the link of the dummy page, and the dummy page is basically allocated heap. It's allocated on this specific position with these two pages. This is the pointer, and this value is crucial because when we are placing this to our iovec array, we don't want to kind of affect our spin lock, and here in comment you can see spin lock in low address half must be 0. So that's why we are putting in the mmap the specific address. Then so this is the 10. In the 10th position is you are controlling your spin lock. On the 10th next 8 byte you're controlling wait queue. I mean, this is again is the wait queue, this is the wait queue spin lock. Inside of wait queue you're controlling your next pointer. Inside of 11th position, the first 8 byte, you're controlling wait queue previous pointer. And here you just want to in this position, in this in these fields, that will be written in this following exploit the address of the task struct. Then you are creating your pipe file descriptor in order to read and write using this pipe, and you have your page buffer where you will, I guess you will, yeah, you will leak data. Then you're forking again. Remember our strategy here. So you're forking inside the child. You're sleeping 2 seconds. While you are sleeping, you are triggering binded threads in order to the structure is freed. Then you are calling write v, which is the blocking syscall, which is like used for reading. So you are using write to read data from kernel. So you are expecting some bytes that will be put to this pipe file descriptor. So it's blocked. Parents process is blocked here. Child after 2 seconds sleep, it's using the freed binded thread using this equals syscall. That's what I told we would consider a little bit later. So you're using this equal syscall with a specific address in order to trigger event poll remove wait queue, and it's go by some call trace. Then you are reading your you are reading this page buffer where you actually place your iovec array here, and this guy is now unblocked, and now you would just want to I mean, here you just like putting your how can I explain? So here you are putting inside of the kernel your what it is. You're putting here the inside of this pipe this kind of payload iovec array, and here you are taking from here. You are putting the writing your dummy data. Inside the dummy data, I mean zeros of iovec array, and on specific positions you are putting your these payloads. So now your data is already written in the right place inside of the kernel, and now you just want to read the leaked data. Your inside of parents. So child's job is done. You can close your pipe and you can exit from child. In the side of process inside of the parents, this guy is unblocked because of this, and now you are reading again from your pipe the leaked page buffer. And now inside of page buffer you have enough space from I don't know if I have this or not. Maybe inside of the inside of the video, I guess. But basically you have now, let me go through where it is. So this guy, Oh yeah. So now inside of this page buffer, what you leaked is inside of 8q. Remember, there are 3 fields: spin lock and the next pref pointer. So you're starting from next pointer. You are leaking enough data until this task struct. So I mean, including task struct. So that's why you can like leak task struct instead of offsetting from this page buffer, instead from here, plus 232 bytes, I guess, in decimal for the task struct. So now you have your leaked task struct pointer. And the second stage is that you're using this task struct, and there is you just want to smash your address limits in order to user can sense and read any data from kernel, and this address limit is now like basically this value. This technique is also very cool because it's also using the same strategy, but the roles are now switched, which means that the roles are now switched, which means that child is not reading here, for example, child here doing read and the parent doing write. Inside of when you want to write inside of the kernel, you are switching these two roles. So child now writes, and the parents doing read, and here in this exploit the read is done using sockets receive message, and just you placing again your inside of the specific location. Again, you just calculate it using offsets, and you're placing your dummy data. These guys are just basically the sum of address lengths of these guys. And this is the values that will be written inside of the address limit that we pointed here. So now, when you smash your address limits, after that you are ready to go to using your exploitation strategy, because you have leaked test tracks, you have smashed address limits, and now you can just go through using these offsets inside of the task struct. For example, you can see there is this structure called inside the task struct. So you first have calculated offset for your then inside of you have user ns, etc. And the symbols are taken from proc.c or from system.map file when you compile your kernel. And after that, just you are free to go with the arbitrary kernel reads and writes. You're reading long, you are reading unsigned long, you are writing where you are writing. Yeah, here you're writing, and after that you have you can do arbitrary kernel reads and writes. So this is basically simple as that, kinda simple as that. I mean, you can check also this exploit using for the Samsung. Again, it's using the same strategy. So you have a bed binder that uses the same offsets, with a little bit kind of difference is that it does not start from the 10th positions. It's starting from the 9th position due to the exploitation strategy. I mean, what it does, and it has also it's also kind of kernel writes memory using again use after free, and you can also leak kernel memory again using the same positions inside of the iovec and doing the same bed binder exploit. So this is briefly it. I mean, this is super briefly, but I will encourage you to check this exploit if you can, and it definitely requires some prerequisites, and for me it's kind of hard, and I guess it's not possible to cover all prerequisites and to explain everything starting from the very beginning, but I tried to do so. Yeah, so hope you enjoy it. Thank you.